This is the first recording of chapter 2 slides. In chapter 2, we are going to study limits and continuity, which is one of the basic concepts in calculus. As you know, derivatives and integral are also based on limits and continuity. First, we will try to see what's the rate of change of a function and tangent lines to the curves. Suppose that an object is moving along the x-axis and its displacement is shown by f of t. Now the average speed of the object between t1 and t2 is the distance traveled divided by elapsed time. F of t2 minus f of t1 is the distance traveled, and t2 minus t1 is the elapsed time. Let's look at this table where f of t is 16t squared. Now t2, let's say t2 is t0 plus h, where t0 is 1. And there's another trial with t0 2. And now t0 plus h shows t2 and t0 shows t1. Now if you put h as 1 and you calculate this difference, for t0 it's 48, and so it's the time is t0 plus 1, that is in the second and third seconds, the average over second and third seconds. At t0 2 it's 2 and 3, so t0 is 2 and t0 plus h3. If you put h is equal to 1, this is 48 and 80. Now as we take h towards 0, at 0.1 the average speed is 33.6 here, 65 over 6 here. When you put h 0.01, it's 32.16 and 64.60. This is the average speed of the object. When you put 0.001, that's 32.016 and 64.016. And as you can see from this figure, the average speed goes to a constant. Like for t0 is equal to 1, the average speed goes to 32.0016. So it's getting close and close to 32, and here it's getting close to 64. Now let's see what we are doing basically here. Actually, you can apply this method for any function. If you have y is equal to f of x, and now delta y is f of x2 minus f of x1, and delta x is equal to x2 minus x1. So this gives you the average rate of change of this function over this time interval. So what we have given as an example can be applied to functions like y is equal to f of x. Now pictorially what we are doing is this. Here is the point on a curve, x1 and f of x1, another point q, x2, f of x2. Now, any line joining 2 points on a curve is called a secant line. And as you can see here, the average rate of change of the function is delta y divided by delta x. So And actually, this is the slope of this second line, because the tangent of theta here is equal to delta y over delta x. So it gives you the slope of the second line. Now, what happens as we approach from Q to P? And that will be important for us. And the previous table that we have shown, it's actually doing that. You have 2 points, this distance is h, and you try to take h towards 0. And what happens if it goes towards 0? This is the picture of a tangent line for the circle. And so let's look at an arbitrary curve. Y is equal to f of x. Between P and Q, you have this second line. And so delta y over delta x for this line gives you the slope of the line. Now, if we move Q towards P, this is the same as taking h towards 0. The slope of the second line, as you can see, changes. And when you are very close to P or at P, you have the tangent line. So the tangent line and the result of course, this would give you the slope of the tangent line. And that's approaching P from the right-hand side. You can have for a curve Q here and P here. And again, that line is the second line. And if you move the point towards P, the slope of the second line changes, and at the end, it becomes the tangent line. And that gives you the slope of the tangent line, which is also called the slope of the curve. Let's look at the same phenomena over y is equal to x squared curve. So our P point is 2, so the y coordinate is 4, because y is equal to x squared. And Q point is 2 plus h, and 2 plus h squared. Y is 2 plus h squared, because y is equal to x squared. So this is the second line. Now when I move Q towards P, the slope of the second line changes, and at the end, it becomes the tangent line. Actually, it's here clearly explained in an algebraic way. That is f of x2, that's this point Q, and if you open this up, the 4's cancel out, and h cancel out. The result of this is h plus 4. So when you take h0, you get the tangent line, and it seems that the tangent line has slope 4. This is another curve. It shows the plot or the graph of the growth of fruit fly population in a controlled experiment. The rate of change in 22 days is 8.6 fly per day. Here the time shows the days in this figure. Now then, if you again have point P and Q, that's the second line. If I move Q towards P, the slope of the second line changes, and at the end it becomes, when you are at P, it becomes the tangent line. Now, so from the previous figures and the tables, we have seen that if you move one point towards the other, you have the tangent line. Let's now give a crude definition of what we mean by limit. Let f of x be defined over an open interval about x0. So this is a symmetric interval, x0 minus h from 0 minus h to x0 plus h. The function may or may not be defined at x0. We are not interested in that. If f of x approaches arbitrarily close to a real number L, for all x sufficiently close to x0, we say that f of x approach to a limit L as x approaches to x sub 0, and write this limit x goes to x sub 0 of f of x is L. That's actually a crude definition of the limit, because we have to put a measure about what does approaches arbitrarily mean, or what does sufficiently close mean. So we'll put a measure on these terminology later on and give a more rigorous definition of the limit. Let's look at these functions. Y is equal to f of x, which is x squared divided by x minus 1. This function is not defined at x equal to 1. As you can see right above 1, we put an open dot here. The function is not defined at this point, because when x is equal to 1, this is 0 and the denominator is 0. So 0 divided by 0 is not a real number, so we cannot put a value here. So in the domain of this function, x is equal to 1 not included. However, if you factorize x squared minus 1, it is x minus 1 multiplied by x plus 1. X minus 1 cancel out. You are left with x plus 1, which is the second function here. And now this function has value 2 at this point, and its limit is 2. As you can see, as we approach 1 from the right-hand side, the limit is 1. As we approach from the left-hand side, the limit is 2. As we approach from the left, the limit is 2. The same is true for this figure. We are not equal to 1, but as x goes to 1 from the right-hand side, again we have limit is equal to 2, or from the left-hand side, again we have limit is equal to 2. So these two functions have the same limit as x goes to 1 from both sides. However, this function is not defined at x equal to 1, whereas this function is defined at x equal to 1. Now let's see algebraically what does this tell us. Here we put x's. This is less than 1, this is greater than 1, this is less, this is greater, this is less, this is greater. So we are approaching x is equal to 1 from both sides. Now, if you calculate the value of this function, you can calculate it as long as x is not equal to 1. So here that's 1.9 if you approach from the left. Here, if you approach from the right, it's 2.1. When I reduce, when I get closer to 1, what happens? Here I'm 0.99 away, so 0.001 away from 1, and I'm 0.01 away from 1 here. Now these two numbers are closer, 1.99, 2.01. And as I approach more to 1 from both sides, the numbers get closer and closer. So as you can see, if I continue like that, if I continue to get close to 1, here as you should notice that I'm not 1. just a little bit different from 1 in the right and in the left. And it's obvious that as you go to 1, the limit is 2. Let's continue. Look at these three functions. The first function is x squared minus 1 divided by x minus 1. That's the one we have seen in the previous slide. Now, this function was not defined at x equal to 1. Now, I set g of x equal to x squared minus 1 over x minus 1 if x is not equal to 1. But at x equal to 1, I put a value here as 1. And as you can see, it's the blue dot here. However, the limit of this function as you approach 1 is the same as this function. As you can see, if you approach from this side, right-hand side, the limit is 2. If you approach from the left-hand side, the limit is again 2. But the function value is not equal to 2. Function value is equal to 1. That's okay. I don't know what I don't care what happens at 1, but I'm interested in what happens as I go towards 1. So that gives me the limit. And this function is x plus 1. So all these three functions, although they are different, they have the same limit as you approach 1. This is the basic idea about the limit. You will approach to a number and you look at your function if it approaches to a constant. And that's the case here. Now, let's look at some simple function. Y is equal to x. The limit at any c is equal to c for this function. So if I approach c from the right or left, it doesn't make any difference. The limit is c again. Now there's a constant function that's simple. Wherever c is, the limit is always k because y is equal to k is a constant function. So at every point c, you have the same limit, k. So these are simple to identify. Now, in certain cases, a function may not have a limit. And the first example is this function. Y is equal to 0 if x is negative. Y is equal to 1 as if x is positive or 0. So as you can see here, when you approach towards 0 from the right-hand side, the limit is 1. But when you approach 0 from the left-hand side, the limit is 0. So there is a jump here, and this limit and this limit are not equal. So this function does not have a limit at 0 because there is a jump in the graph of the function. Now let's look at this function. Y is equal to 1 over x if x is not 0. Y is equal to 0 if x is 0. Now this function is defined for all real numbers. However, as x goes towards 0 from the right-hand side here, your function grows too much. You cannot give me any limit because any big number you give me for the limit, I can find an interval on the right of 0 so that the function value is greater than this number. So since this number grows too much, it doesn't have any limit. You cannot put a limit on a growing function, always growing function. And let's look at the left-hand side. Here, the function gets smaller too much. It's a big absolute value of the negative number is big, and you cannot put a limit on this side too. So this function is does not have a limit at x equal to 0. Another example is y is equal to sine 1 over x for x greater than 0, 0 for x less than 0, less than or equal to 0. So this function is also defined everywhere. Number goes towards 0, as you can see here from the right-hand side, the function oscillates too much. The frequency increases infinitely, and you cannot give any limit here, because I can always find a small interval where the function value is not cannot stay in the same place. So if it oscillates too much, it's difficult to find the limit for this function. It's impossible, actually. So this function oscillates too much, this function grows too much, and this function has a jump at x of 0. So all these three functions do not have limits at x equal to 0. Let's look at the limit laws. It's clear by the definition of the limit. Now, if you have two functions, f of x, which has a limit as x approaches to c, L, and another function, g of x, which as x approaches to c has limit m. So sum rule is, if you have f of x plus g of x, the limit of the sum is sum of the limits. Similarly, difference of the functions, the limit of the difference of the functions is the difference of the limit. If you multiply a function with a constant, the limit of this function, again, as x approaches to c, is k times L. If you multiply two functions, the limit of the multiplication of the function is multiplication of the limits. Same is true for division. Of course, m should not be 0 here in order to define this limit. So the ratio of the functions, the limit of the ratio of the functions is the ratio of the limits. Power of the function f of x, the limit of the power of the f of x is power of the limit for n positive integer. Now, root of the function, nth root of the function, has a limit, nth root of the limit. And that's 1 over n. Of course, if this is a real number, L to the root n is a real number. Because, for instance, if L is negative and n is 2, negative square root of negative of number is not defined here. Okay, so these are the limit laws. We'll give a proof of one or two of them, but most of it is obvious from the definition. Okay, limits of polynomials. Now here you can just directly substitute the limit of p of x as x approaches to c is p of c. You just, instead of x, you just substitute. So there is no problem here, and you can find it immediately. The limit of a rational function can also be find by substitution if there is no problem. For instance, for this rational function, denominator is never 0, so there is no problem, and you can just substitute c, that will give you the limit. In certain cases, there might be a problem in the denominator polynomial. Here, what you can do is see if you can cancel out the 0 divisor. or the zero denominator. You can factorize this as x times x minus 1, and the upper part is x plus 2 times x minus 1. So x minus 1 cancel out. As long as x is not equal to 1, you don't have a problem in canceling x minus 1. When x is equal to 1, you cannot cancel it. But in the limit, we are not interested in what happened as x equal to 1. We are interested in how my function behaves as x approaches 1. That gives us the limit. So when you cancel out, you have this. So I write here limit as x approaches to 1 is equal to 3, because 1 plus 2 is 3, this is 1, so that's equal to 3. In certain cases, you can cancel out the common factor by multiplying with 1. That's a typical example. Limit as x goes to 0 of x squared plus 100 minus 10. At x of x equal to 0, this is 0 and this is 0 also. So 0 divided by 0 is not a real number. So what I do is I multiply this expression by 1. If you remember constant multiple rule, the limit doesn't change with respect to constant multiple rule. So I multiply by x squared plus 100 in the square root plus 10, and also divide by the same number. So that's equal to multiplying the expression by 1. But when I calculate, I have 100 goes cancels out. I have x squared here, and I have x squared here. As long as I'm not 0, I can cancel these x squares. So the result is 1 over x squared plus 100 in the square root and plus 10. So I can put x is equal to 0 now, and that gives us 1 over 20 as the limit. So the rational functions, the limit of rational functions can be calculated in this way. Let's see what happens here graphically. Okay, the same function here. This function is not defined at x equal to 1. But if you look at the curve, as I approach 1 from the left-hand side, the limit is 3. As I approach 1 from the right-hand side, the limit is 3. So the limit of this function is 3 as I approach 1. Of course, we have an open dot again here because the function is not defined at this point. After the cancellation of the 0 denominator, I am left with this function. Now this function is defined at 1. It has a value 3, which is also the limit of the function. Let's continue. Okay, so that's, you can see 3 functions here. The red function is h, blue function is f, yellow function is g. As you can see here, f is less than h and greater than g, all in this interval. So f is squeezed between h and g. But you can see also that as you approach c, either from the left-hand side or from the right-hand side, h and g has limit L. They have the same limit. Then we conclude that f must have the same limit too. This is a pictorial representation of what we call a sandwich theorem. So the sandwich theorem is useful in the sense that if you can squeeze the function in an interval between 2 functions that have the same limit, then your function must have the same limit also. We are going to use this sandwich theorem later on. That's the statement of the theorem. Suppose that g of x, f of x, h of x for all x in an open interval containing C, they satisfy this inequality. At x equal to C, this inequality may be satisfied or may not be satisfied. We don't care. But for all other x, this inequality must be satisfied. And if the limit of g of x as x goes to C equal to limit of h of x as x goes to C, and which is equal to L, then the limit of f of x is equal to L. That's how the sandwich theorem is stated. As I said, we are going to use this theorem later on. And that's another pictorial representation of the sandwich theorem. You have y is equal to 1 plus x squared over 2. That's a parabola open and upwards, and at 0 it is equal to 1. Here another function, yellow function, y is equal to 1 minus x squared over 4, which is parabola again opening downwards. And now you have a function u of x, which is squeezed between these functions. So u of x must have limit 1 as x approaches to 0, both from the right and both from the left. The limit must be equal to 1 because these functions have limit 1 as x approaches to 0. Another example for the sandwich theorem is y is equal to sine theta. Y is equal to sine theta is less than y is equal to absolute value of theta over this interval between minus pi and plus pi. Now y is equal to minus the absolute value of theta is less than y is equal to sine theta, which is this function here. So sine theta is squeezed between these two functions over this interval. Another example still is y is equal to absolute value of theta. Here y is equal to 1 minus cosine theta, and the yellow function is y is equal to 0. Now y is equal to 1 minus cosine theta is squeezed between y is equal to absolute value of theta and y is equal to 0. So when you approach 0, this function must have the same limit as this function, both from the right and from left, and for this function also. All these three functions have limit 0 as theta approaches to 0. That's another demonstration of the sandwich theorem. Okay, so these were some examples about the limits, but the definition we gave for the limit was a crude one. I mean, what do we mean by arbitrarily approaching to a number? What do we mean by sufficiently close to a real number? We have to put a measure on that, and that's what the precise definition of limit gives us. Let f of x be defined on an open interval about C, except possibly at C itself. So that means f of x may or may not be defined at C, I don't care. We say that the limit of f of x as x approaches C is the number L, and write this expression, limit f of x as x approaches C is equal to L. Now, what's the condition? For every real number, positive real number greater than 0, we have to find a delta greater than 0, such that whenever x is in this interval, except C, x is equal to C, when x is in this interval, this must be true. Now, epsilon gives you a definition of arbitrary approaching to L, this gives a definition of sufficiently close to C. Okay, so that's a measure for these concepts, and that's the rigorous definition or mathematical definition of the limit. So in order to write this expression, limit f of x as x approaches to C is equal to L, I have to show you that for every epsilon you give me, I can find a delta. So for all x in this interval, that's a symmetric interval around C, f of x minus L must be epsilon. If I can show you this, then I can write this expression. That's the proof that L is the limit of this function at x equal C. Let's look at this precise definition and try to prove certain limits that we already know. Our function is y is equal to x minus 1, and we are going to look at the limit as x equal to as x approaches to 4. So C is 4 here, f of x is 2x minus 1. Obvious that this 7 is the limit of this function as x approaches to 4. So if you give me any epsilon, it might be as small as you want, it doesn't matter. I have to find you a delta. So algebraically, I start like this. Y minus 7. Y is equal to f of x, which is 2x minus 1. L is the limit 7. So this inequality is equivalent to this inequality, because I substitute for y here, minus 7 here. So this equality, it's also equal to this. Minus epsilon is less than 2x minus 1 minus 7, which is less than epsilon. So this. Now I can add to each side 8. So I have minus epsilon plus 8 is less than 2x, which is less than epsilon plus 8. I can divide by 2. The inequality doesn't change. Minus epsilon over 2 plus 4 is less than x, which is less than epsilon over 2 plus 4. Now I want to find at this point a symmetric interval about 4. So I subtract 4 from each side. So I have minus epsilon over 2, x minus 4 is plus epsilon over 2. Now that's a symmetric interval about 4, because the distance to this end is epsilon over 2. The distance to this end is epsilon over 2. Although that's a negative number, it doesn't make. Its absolute value shows you the distance from the origin. So what I choose for delta is epsilon over 2. So I can do this for any epsilon you give me. So that's a proof that the limit of y is equal to 2x minus 1 as x approaches to 4 is 7. Okay. So that's finding delta algebraically. Let's give another example that's sort of similar. Our function is 5x minus 3, and we are going to look at the limit as x approaches 1. It's obvious that this is equal to 2. But still, if you're asked to prove that, you have to, for each epsilon given, you have to find a delta, which is a function of epsilon, so that whenever x minus 1 is in this, x is in this interval, this must hold. That's f of x minus L, must be less than epsilon. Now it's easy to find this because this is f of x 5x minus 3 minus L. less than epsilon, I can open it like this. I can take 5 out. I have 5 times absolute value of x minus 1. So that's a symmetric interval if I divide by 5. So x minus 1 is less than epsilon over 5, which I choose as delta. I can choose a smaller one. It would do it also, but that's the maximum delta I can find. So that for all x in this interval, this holds, except x equal to 1. Because I don't care what happens at x equal to 1. But for all other x in this symmetric interval about 1, this must hold. When I show that, then it's the proof. Okay, so that's how we find algebraically. You can do this geometrically. Also, that's a simple function. Here, as you can see, epsilon is given as 2. The limit is 7. So when you're given an epsilon, you find this place. Your function value must be within this place because it will be less than epsilon. So how can I find delta? Delta is epsilon over 2, so delta is 1. So when 4 is between 3 and 5, I mean, for all x intervals in this interval, the function value must be in this interval on y-axis. So you ask me the interval epsilon, you give me the epsilon, then I find delta geometrically like this. You first, this is L plus epsilon, this is L minus epsilon, epsilon is equal to 2. So for any interval I choose around 4, this must hold. The function value must be between these limits. As you can see, I can choose a smaller one, smaller delta. That's smaller than epsilon over 2 or smaller than 1. That will still do, but the maximum delta you will find is 1. If you find a larger symmetric interval, you will be out of this limit. Your function value will be out of these limits. So that means f of x minus L is not less than epsilon. So that's the geometrical way of finding delta. That picture also tells you what to do. You are given, in this case, L is 1 over 10. Epsilon is 1 over 10, sorry. So L is this point, the limit of the function. I want to prove that it should be this point. So that's L plus epsilon, L minus epsilon. Now C is here. I choose a symmetric interval around C. And for all x here, my function value must be within these two limits. Okay, so that's, I know we have shown that how to find algebraically, but that's how you find geometrically. Let's continue. Okay, that's the second function we deal with. Suppose you give me epsilon, and I want to prove that the limit is 2 as x approaches 1. So you just draw a horizontal line from 2 plus epsilon and 2 minus epsilon. And that's your delta. Epsilon over 5 is your delta. And that's a symmetric interval because this line, the distance from 1 is equal to epsilon over 5, and distance from here to here is epsilon over 5. So that's a symmetric interval around 1. That's the maximum delta you can choose. You can choose a smaller one. You can choose an interval around here. That will do also. But it's important to find the maximum delta, because if you choose anything larger, your function value is not within this limits, as you can see. If I choose this point as the end of the interval, you're out of the range. Or if I choose this point, you're out of the range. So f of x minus L less than epsilon is not true if you go beyond these limits. Oops, sorry. Okay, y is equal to x. That's the given thing. It's always c. Now, if you are given an epsilon, that's c plus epsilon and c minus epsilon, okay? You can choose delta so that your interval is this. So that's the same length on the right and on the left. That's what symmetric means. Like from this to this point and this to this point must be the same. You can choose a smaller one as shown here because it satisfies our horizontal line is here and here. So, or you can choose the maximum one. In this case, delta is equal to epsilon. Okay. Now that's the constant function. Now you can choose any delta here. If you give me epsilon, I can choose any delta. It doesn't make any difference. I can choose a larger one and a smaller one, but that's only for the constant function. You cannot do that for the other functions. Any delta would do in this case. Any delta would work. Now let's look at this function. Y is equal to square root of x minus 1. Now I want to prove that the limit of this function as x approaches 5 is equal to 2. When I approach x, as x approaches 5, from right hand side or left hand side, the limit is 2. We will do that algebraically, but as you can see here, on the left hand side, we have an interval of length 3. Okay, so whenever my x is here, I'm satisfied. F of x minus L, that's square root of x minus 1 minus 2, is less than the given epsilon. In this case, as you can see, epsilon is equal to 1. Now, on the right-hand side, though, I have an interval of length 5. And if x is here, then I'm in this region again. F of x minus L less than epsilon again. But on the right-hand side, not on the left-hand side. So what shall I choose as delta? I choose delta as 3. Okay, that's 3 different, 3 greater than 5, 3 less than 5. Because if I choose 5, I'm out of the range. So in the inequality, when you have a right and left different leg, you should choose the minimum one, as we did here. So we choose this. That's 3. We did not choose 5 here. Okay, so that's the basic idea about proving the limit. So let's do this algebraically. Now, let's write f of x minus L, that's square root of x minus 1 minus 2, because 2 is the limit, L. Now, this inequality is equivalent to this inequality. Minus epsilon is less than square root of x minus 1, which is minus 2, which is less than epsilon. Now I can add 2 to each side, so I have this inequality. The same as this one and same as this one. I mean, from here I can go backwards here, or here looking forward, go to this. Now, right now, if we assume that epsilon is less than 2, we can take the squares easily, and inequality will not change. So let's take the squares and add 1. So I have 2 minus epsilon squared plus 1 here, which is less than x. 2 plus epsilon squared plus 1 here. I assume that epsilon less than 1. Now, now the limit 5 is c here as I approach 5. So what I'm going to do is I subtract 5 from each side. So I have 2 minus epsilon squared minus 4, x minus 5, 2 plus epsilon squared minus 4. Now, if epsilon is, as you can see in this figure, let's put that, epsilon is equal to 1 in this case, in this figure. So if you substitute that, epsilon is equal to 1. Now, as you can see, this is 2 minus 1 squared, that's 1. That's minus 3. 2 plus 1 squared, that's 9. Minus 4, 5. So I have on the right side 5, on the left-hand side 3, like in the figure. But that's true for every epsilon you give me, because I didn't give any value to epsilon yet. So if you open this up, that's epsilon times epsilon minus 4. That's epsilon times epsilon plus 4. Now, as you can see, this is a negative number, but it doesn't make any difference because I'm going to take the absolute value. I'm looking at the distance from 5. So if it's 1, it's minus 3. So the distance from 5 is 3 here. The same here. Distance from 3 is 5. Distance from 5 is 5 here, actually. So what I choose is this, the minimum one. X minus 5, absolute value must be less than this. If you calculate this for epsilon 1, that's 3. If you calculate for epsilon 1, that's 5. So I don't choose this, I choose this. Because if I choose this, I will go, let me show you in the figure, I will go this way. I will be out of here. So my function value will not be between these two values, which is epsilon plus 1, epsilon L plus epsilon and L minus epsilon. Okay, so that's the basic idea, proving that the limit of a function is something. This is sort of a summary of the algebraic way you solve this inequality. And you obtain from this inequality an inequality that's for x. And then you choose the delta in the way we explain. Okay, let's look at y is equal to x squared. And now that's a function, as you can see. Y is equal to x squared if x is not equal to 2. At x equal to 2, the function value is 1. So, but I'm not interested in what happens at x equal to 2. I look at what happens as I approach from the right and from the left. What's the limit? The limit is 4 here, okay? So the value of this function, the limit of this function as x approaches to 2 is 4, although the function value is 1. We can also show this algebraically. Okay, that's our function. F of x is equal to x squared if x is not equal to 2. F of x is equal to 2 if x is equal to 2. That should be 1. That's a misprint here. Now we have to show that the limit as x approaches to 2 is f of x is 4. Now we write the f of x minus L is this. I want this to be less than epsilon. I open this up. I have minus epsilon less than x squared minus 4, which is less than plus epsilon. Now I can add 4 each side. So 4 minus epsilon, x squared is less than 4 minus epsilon, which is less than 4 plus epsilon, as shown in the figure here. Okay, so what I do is I have to subtract 2 from each side so that I will have x minus 2 here. Then I'm going to look at the distance on the left side and distance on the right side. Okay, as you can see, if I subtract 2 from each side, 4 minus epsilon minus 2 is a negative number. But I'll look at the absolute value. That will give me the distance. 4 plus epsilon, square root of 4 plus epsilon minus 2 is a positive number, definitely. So the absolute value of this 2 minus 4 minus epsilon. And the absolute value of this is equal to itself because that's a positive number. So 4 plus epsilon minus 2 is the distance on the right side. 2 minus square root of 4 minus epsilon is the distance on the left-hand side. Then we get f of x minus 4 is less than epsilon, and my delta is the minimum. For each epsilon, I have to calculate the distance from 2, and then I'll choose the minimum one. Okay? Let's continue. Now, that example is limits, one of the limit rules. If you have two functions, one is f of x with limit Lx goes to c, and another function with limit m as x goes to c. So f of x and g of x are functions who have limits as x approaches to c. Now, what I have to prove that f of x plus g of x, the limit as x approaches to c, is the sum of the limits of the individual functions. So for any given epsilon, I have to find delta such that for all x in this interval except c itself, f of x plus g of x minus L minus m must be less than epsilon. Now, here is f of x minus L, f of x plus g of x minus L minus m. And that's equal to, I can write it like this, f of x minus L plus g of x minus m. Then this is less than or equal to, because the triangle law of absolute value, f of x minus L, g of x minus m. That's less than or equal to that. Now, since these functions have limits, so they have delta for each epsilon. So let's say delta is delta for the first function, so that f of x minus L less than epsilon over 2. So instead of epsilon, I give epsilon over 2, and there must exist a delta 1 because the functions have limit. And for the second function, let's say it's delta 2. When the x is in this interval, g of x minus m is again less than epsilon over 2. So this is epsilon over 2 plus epsilon over 2, which is telling me f of x plus g of x minus L minus m is less than the given epsilon. What I choose for delta is the minimum of delta 1 and delta 2. Minimum of the deltas of two functions, actually. That's another theorem which we are going to give the proof. Limit, suppose that limit as x goes to c of f of x is L. like here, and limit x goes of c, g of x is m. And f of x and g of x satisfy this inequality over an open interval about c, except possibly c itself. It may or it may not satisfy this inequality at c. I don't care about it. Now, we have to prove that L is less than or equal to M. That means if f of x is less than or equal to g of x, that means M is less than or equal, M is greater than or equal to L. Let's prove this. Suppose that this is the given condition. Suppose that L is greater than M. I just assume the opposite. And limit as x goes to c, g of x minus f of x. I choose m minus L for any epsilon. Okay, we assume first that L is greater than M, and for epsilon, I give L minus M for epsilon. Now, g of x minus f of x minus M minus L, because this is the difference, it's the difference of the limits, g of x minus f of x, which is a positive number. M minus L is the limit by the limit rules of limits. I want this to be less than. So I choose epsilon as L minus M, because I assume that I just assume the opposite of this. L is greater than I assumed. So since it's greater than M, L minus M must be epsilon. I choose epsilon as L minus M. So let's continue. So g of x minus f of x minus M minus L must be less than L minus M. That's my epsilon I choose. But this is a positive number. If you open this and that's equal to, and since L is greater than M, that's a positive number too, because I assume that L is greater than. So this is a positive number in total. So I can forget about the absolute value, because absolute value of a positive number, it's equal to itself. Now, as you can see here, M's cancel out here, L's cancel out here. That tells me g of x must be less than f of x, which contradicts the hypothesis, okay? Because if these cancel out, we have 0 here, g of x minus f of x here is less than 0, must be less than 0 if I choose epsilon as L minus M. So that's a contradiction, and so that cannot happen, because the hypothesis says that f of x is less than or equal to g of x. But here we get f of x is greater than g of x. Okay, so that's the proof. Because of the contradiction, this is not possible. So that must be true. Let's continue. Okay, so we'll give a break at section 2.4. That's one-sided limits. I will later on record the remaining of chapter 2 and try to finish chapter 2.